kind of our foray to study some electron hydrodynamics effects. In particular, what we're calling beyond Ohm's law, namely looking for nonlinear signatures that are distinctive in a hydrodynamic regime. So this was work done in collaboration with Sam, Vadim, and Una, which led to 2 papers. So I'll be primarily talking about this archive paper below here. Right. So I guess just as a refresher, when we talk about transport in condensed matter systems, we typically divide up regimes of transport based on the type of scattering that is dominant in the system. So for instance, when electron impurity scattering length is very short, we call this diffusive transport. This is typical conductive, where the carrier particles hits impurities and executes some random walk. When electron boundary scattering is the shortest, we call this ballistic, and the particle just bounces off walls. And then finally, when electron-electron scattering is the shortest, length is the shortest, we call this hydrodynamic. And the particles are colliding with one another a lot, and so interactions are very strong. And you need typically to have ultra clean samples to realize such a regime. And so, of course, this hydrodynamic regime is the regime that we're going to be interested in talking about today. And electron hydrodynamics has been around for a long time, being used as a framework to study strongly correlated systems. So in the past, the quantities that people have looked at, as far as observables go, are primarily local in nature. Things like DC conductivity, thermal conductivity, Wiedemann-Franz ratios, etc. But more recently, we've begun to become interested in these viscous effects, which lead to non-local.
You hear me?
Sorry. Yep. Hello. Okay. I guess I'll just continue that. Yeah. So we've been interested in viscous effects, which leads to non-local transport behavior. And there are a lot of kind of everyday common experiences we have of these viscous effects. For instance, when you pour honey out of a jar, you immediately experience the viscous flow resistance. Or if you look at air behind the wing of an airplane, you can generate vortical type shapes. And what has made this field particularly excitingly recently is the fact that some of these classical striking examples of non-local transport behavior have begun to be measured in some of these electron hydrodynamics experiments. For instance, people have measured vortex formation by looking at negative non-local resistances, or looking at resistances and finding that they're negative. By looking at the channel width dependence of the resistivity, people have found deviations away from ohmic behavior in signifying some kind of non-local or viscous type fluid flow. And there have also been experiments which have looked to measure directly the flow profiles inside rectangular type geometries, and they've observed positional dependence of this current that seems parabolic in nature, very reminiscent of Poisson flow. And so this is just a few of the experiments that people have been doing recently. But all of these effects can be simply understood by the phenomenological description of a linearized Navier-Stokes equation. And because it's a linearized Navier-Stokes equation, the generative equation is quite simple. Namely, you have some electric field, which is the analogous term for pressure gradient, and then you have some shear viscosity term, which comes in with 2 powers of the gradient here. There's one additional term that you need to make this electron hydrodynamics, and that is a finite resistivity. Any real material is going to have relaxed momentum at least a little bit. And so, what people do is you put in the scattering rate by hand, gamma, into the Stokes equation. It'll be convenient for us to talk about this equation instead in terms of conductivities. So we can go ahead and invert the above equation at long wavelength. And so you have the sigma naught term, which corresponds to the scattering rate, and sigma 2 term, which corresponds roughly to the viscosity. And if you look at these equations, what you find is that there's a natural length scale that emerges, namely the viscosity, what we call the viscosity length scale, RD, given by the ratio between sigma 2 to sigma naught, or nu to gamma. And it is precisely this length scale which tells you about the strength of viscous effects. So in a rectangular profile, rectangular geometry, where W is the width of the channel, when RD is very small, you'll recover a rectangular ohmic profile, whereas when RD is very large compared to the channel width, you'll recover the parabolic flow profile of Postel flow. Moreover, in these current injection geometries where you generate these vortices, RD is what controls the radius of the vortex. This is some nice results from this equation, and one can take a step back from this equation and kind of forget all the hydrodynamic stuff and just stare at this for a bit. And what you realize is that, well, this is nothing more than a statement of Ohm's law, with the extra wrinkle that instead of a momentum independent conductivity, you have some sigma 2 term giving you some momentum dependence, right? And this immediately raises the question, whether or not observing a finite sigma 2 is sufficient to say that you're in some electron scattering dominated regime, right? Ohm's law, even a momentum dependent Ohm's law, could come from a variety of sources, and it at least a priori doesn't necessarily seem indicative of a hydrodynamic regime. And so to understand the origin of where you could get these non-local effects, where you could get this finite viscosity looking term, in this paper,
this is zero temperature still, correct?
Yeah, this is zero temperature. This is zero temperature. That's right. Right. So
but the measurements are done at finite temperature, right?
That's right. So yeah, so this is just kind of a. Oh, sorry, did you say something?
No. I mean, are you trying to say? I mean, what is the connection? I mean, you are saying that there is some non-locality that give a length scale that looks like, let's say Gurgy lens, but yet this is zero temperature, and there are signatures that are not seen at lowest temperatures, and so some experimental signatures of hydro regime typically going to, I don't know, regime of 50, 70, and so on temperature. Right. So this approach doesn't capture any temperature dependence. That's what I'm saying.
No. Right. That's right. Right. But kind of the point is that right. So if you're just so I guess if you look at temperature dependence, like if you or how do I want to say this? The phenomenological observation of these non-local signatures in and of itself is not enough. As you're saying, if you had extra parameters such as temperature, magnetic field, carrier density, etc., in which you could actually distinguish different mechanisms of scattering, then of course you can say something about whether or not you're in the hydrodynamic regime or not. I guess that's jumping ahead a little bit, but that's kind of the point I'm trying to make here. Yeah. Right. So if
can you repeat for a second? What's non-local so far?
not, but by non-local, all I mean is that you have some momentum dependence that is characterizing the effect that you're interested in studying. So
I think that people may be still thinking that this term that you wrote is an actual viscosity, which is not, as far as I'm concerned, correct? So this is just some constant piece that you are referring from your bubble, correct? So it's just a coefficient of expanding Kubo formula to Q square order.
Right. No. So this, what I'm saying is the sigma 2 is essentially equivalent to your viscosity.
But what do you mean essentially equivalent? I mean, this is just a coefficient of the Kubo formula. It has no temperature dependence. It looks like, but it has nothing to do with
a viscosity. Yeah, it looks like a viscosity. That's right. Sorry, did that answer your question?
Would that equation look different in the case of usual diffusion?
In the case of usual, let's see. So in typical diffusion, you would, sorry, I'm like thinking about this on the spot. In typical diffusion, well, okay, let me put it this way. The equation that I'm about to talk about is essentially, the system I'm about to talk about is essentially diffusion of electrons. It's going to be a model in which all you have is electrons scattering off impurities. I guess it's not quite classical diffusion, but this is precisely what you will be getting in a long wavelength expansion of that model.
Okay, but if you have just electrons scattering off impurities, then there is no viscosity.
That's right. That's right. Yeah. In the strict sense, you won't have viscosity, but what I'm saying is that you'll have these non-local effects that at least at this level looks very similar. That's right.
Okay.
Mm-hmm. Yeah. Okay. Right. So, okay. So, right, the model that I've written down here is just a fermion kinetic energy coupled to Gaussian disorder, zero temperature. And you do the standard thing where you calculate the conductivities using a Kubo formula, and and then you do this expansion to Q squared order. Now, this, as far as we know, this calculation surprisingly hadn't been done before. So we would just go at least in 2+1D, and we're going to just go ahead and evaluate that numerically. Okay. So this is the result that you get. Yeah.
Can I also ask a quick question? So you're writing that vertex corrections are vanishing. Is like, I mean, they usually don't, right?
Yeah, that's right.
And sorry, could you clarify the statement that it hasn't been done? What exactly? The bare bubble hasn't been done?
The bubble has been done. The calculation to Q squared order hasn't been done.
But I know that even people calculated weak localization corrections to it. And actually, Q scaling up to high order, what do you mean it hasn't been done?
So, as far as I know, it hasn't been done. If you have papers that calculate this, I would love to know. Sure. Yeah.
I would say this bubble without vertex correction has certainly been done.
Yeah.
Boris, as you know, even with vertex corrections, it's been done.
Well, even with vertex correction, yeah.
Yeah. If you're aware of papers, please send them my way. Many people have made this comment to us, but we have not been able to find papers, nor have people sent papers to have been able to send papers to us. So, but anyways, right. So what you find when you do this is, as you would expect, that this viscous length scale is actually surprisingly non-zero. So you'll end up seeing these non-local transport features, even though technically you have no viscosity, no hydrodynamics in the system. So you'll see very similar non-local measure effects and measurements, even when you're not in a hydrodynamic regime. And indeed, this is because your viscous length scale, RD, ends up being controlled by the impurity mean free path. And so what, as many of you have mentioned already, the sigma 2 parameter that is controlling these non-local effects is getting length scales contributions not just from electron-electron scattering, but in this case, electron impurity scattering. And so, it becomes a challenge, or you need to know more microscopic, say, temperature dependence, what have you, to really isolate the electron-electron scattering mechanism from, say, electron impurity and other things.
I'm getting a bit confused. So you're saying that you have this coefficient, this sigma 2, that is not viscosity because there's no electron-electron interaction.
Right.
So how is it different from the usual diffusion coefficient?
How is it different from usual diffusion? I mean, usual diffusion is, so if, right, if I have just, right, I don't want to say this. I mean, usual diffusion, like particle, if I just have electrons executing random walk, it should just be DC conductivity, right? So the fact that I have, some momentum dependence of, yeah, maybe I shouldn't be trying to figure this out on the fly.
No, maybe what you want to say is that you have a finite frequency, so that is like a really conductivity, right? So you expand the conductivity here.
Right. No, so, momentum, but yeah.
Right, so,
yeah, right.
Okay. Does it go as Q times some Q by KF or Q by mean free times mean free path? What is the dependence?
Right. The Q goes with here. It goes with, I believe it goes with mean free path. Yeah.
Thank you.
I mean, free path is basically the diffusion coefficient, right?
Right.
So then the non-local effects you're talking about is just this sort of non-local conductivity, which you find by sort of modulating the applied electric field, right?
Sure. Yeah. Or have some current injection points. Right. Yeah. So you modulate the electric field in some way by applying whatever contacts, and then you see some vortex behavior, parabolic flow type behavior, stuff like that.
Okay.
Okay. So yeah, thanks for all the questions. Right. So kind of to think about how these various mechanisms might contribute to these non-local transport features, and distinguishing them in microscopics is definitely a very interesting one, but they're also very involved, and seems it seems a bit difficult. So what we decided to do instead is to take a step back and ask a high-level question of how exactly is Navier-Stokes different from kind of this Ohm's law description, where you're looking at the sigma 2 coefficient and how viscosity or other things may be contributing. So let me remind you of how the Navier-Stokes equation looks. on the left here, you have this dp dt term, momentum derivative, and then on the right you have the collection of forces that act on my this momentum equation. And what is interesting about the Navier-Stokes equation, particularly for us, is that you get this convection term because velocity is a field. There's a convection term coming from the fact that you need to conserve momentum fluxes. And it is precisely these two powers of velocity which drives you outside of this linear regime and will give rise to the physics that I'll be discussing. On the right, we have typical terms such as pressure, shear and bulk viscosities. These are the gray terms. And then the terms in green are those specific to the electronic system, namely, you have an electric force because particles are charged, and then again the resistivity. So it'll be convenient for us to think of convection as a effective force. And when we there's something called the Reynolds number, which is a dimensionless quantity, you generally use to characterize how strong the nonlinearities are in a fluid, and this is defined precisely as the strength of the convective force to the shear viscosity. And well, of course, these quantities are position dependent and complicated and require you to solve. So what you do is you take dimensional analysis estimates to try to get a handle of how nonlinear or how strong the nonlinearities are in the system. So typically when people talk about nonlinearities in fluid mechanics, you talk about turbulence setting in around like 3,000 and very high Reynolds numbers. That is not the regime we're working in. We're going to primarily be working at perturbatively low Reynolds numbers, say 1/1000. But even there, you'll see some interesting stuff happen. In addition to this Reynolds number that typically is written down in fluid mechanics, there's additional dimensionless number, Reynolds-like number, which is the ratio of the convection force to the resistivity. And this term also turns out to be important in characterizing the strength of nonlinearities in the system. And so what you want to have strong linearities is both of these numbers to be large. And so the smaller one will be the one that ends up dominating the physics in your system. So the ratio of these is given by the viscous length scale compared to some scale of the system. And for devices that are order 10 micrometers, and we typically have, say in graphene, this viscous length scale to be 1 micrometer. And well, what this means is that this Re gamma will be the one that's typically smaller and be the one that's typically dominating. And so what this means is that in contrast to a lot of previous proposals for looking at viscosity to be a signature of hydrodynamics, here we're proposing, since we're proposing convection to be the signature, it turns out that viscosity kind of plays a subleading role, and it's the interplay between viscosity and gamma that matters. Okay, so now we can turn to some of the effects that we are proposing. So the first one, and indeed the prototypical example of the Bernoulli effect, the convective nonlinearities, is known as the Bernoulli effect. And so if you ever played with a hose or your sink, and if you put your thumb on the aperture and close it a little bit, the water will spew out at a much increased rate as a result of mass flow conservation. Now, in this Venturi geometry, as you keep track of the velocity into the constriction and the pressure into the constriction, you'll find that as the velocity goes up, the pressure goes down. And this is a statement of energy conservation. And of course, this energy conservation statement can be understood as coming from the Navier-Stokes by integrating it, where I remarked that this kinetic term is coming from the convection term. Now, this is kind of an innocuous statement of energy conservation in the classical setting, but if you translate these variables and the system to the electron hydrodynamic setting, where pressure is equivalent to a voltage and velocity is equivalent to a current, and design a similar type of construction, this becomes a non-trivial statement that you'll expect to see a nonlinear IV characteristic simply from the fact that the electron's in a hydrodynamic regime. Namely that the voltage will go as I squared, or if you like, the current goes as the square root of V. So you can go ahead and just run the math of solving Navier-Stokes to see what you get for the IV characteristic. So to do this analytically, we're going to neglect viscosity for now, and then we're going to assume that our flow profile is completely radial, that there's no theta components to it. And so this is what you get. You get a linear Juda term, which is what you would normally expect to get for a resistor in this shape. And then you have the Bernoulli contribution here, highlighted in blue, which is quadratic in I. And as such, you get this tilted parabola where you have a stable branch as it goes through the origin here in blue, and then you have an unstable branch in gray. And then you have some critical V naught below which this radial ansatz breaks down. And the reason this breaks down is known because in this regime, you have strong divergent flow. So the particles are going from left to right in this wedge. And it's known that if the flow is too strong, then you'll have a breakdown towards turbulent behavior.
Could I ask for clarification?
Yeah.
In sigma d has a 1 over gamma, right? Which is why you're calling the first term the Juda term, and not the second one. Okay.
Yeah.
Thank you.
That's right. Yeah.
So, can I just ask a question? If you don't think about sort of Navier-Stokes equation, but if you're just thinking about the regular transport theory, right?
Sure.
You can also find nonlinear terms.
Right.
So you have the Ohm's law, but that's linear, but then you can do nonlinear response as well.
Sure.
So here you seem to be getting some nonlinear terms from the sort of hydrodynamic part.
That's right.
Of the equation, but you don't take into account the regular sort of disorder transport nonlinearity.
That's right.
How are the two compared?
Right. So that, I guess that segues into the next point. Like, how do you, what I was about to get to, which is how do you isolate this term from, say, other nonlinearities? And the functional form of this is pretty unique, and should help in distinguishing it from other types of nonlinearities, say like from disorder or whatever. The first thing is that if you look at the geometrical features of this, it's length independent, and only depends on H0 and H1, so which are the input and output radii. So as compared to, say, any nonlinearities that may come from disorder, you could imagine making the device longer, or changing the angle of this wedge to try to have some try to control it and see geometric dependencies that are characteristic of this Bernoulli term. In particular, this Bernoulli term will vanish if it's a rectangular geometry. So as long as you don't have other you can look for geometric type effects when you go from a rectangle to a wedge, and look for this this 1 over h naught squared type behavior. And then also this Bernoulli term depends on the charge density. So one could imagine flipping the sign of this Bernoulli term by changing the carrier type from electrons to holes, for example, while maintaining a fixed current. Yeah, so hopefully that answers your question. Right. So to get a sense of how strong this is in a realistic device, here we're going to take graphene as our model. And these are we're going to do some numerical estimates where we're not making this radial assumption. We're going to put back in viscosity. And so here we have the IV characteristic. And then we have I've plotted the symmetric current fraction against the total current, where the symmetric current fraction is a measure of how nonlinear the IV characteristic is. And we have device parameters on the order of 10 micrometers. So these points are the numerical data, and then the lines are the analytical result from before. And as I've tried to argue to you, and is again shown here, the neglect of viscosity in doing this calculation is a pretty good assumption. And so what you get at the end of the day is that you expect current deviations from linearity of about 400 nanoamps for about 200 microamps of input current. Or if you like thinking of it in terms of Reynolds numbers, this is about 1 over 1,000.
And what's the carrier density in this calculation?
Carrier density is at 10 to the 12 per. It is typical graphene carrier density. Yeah.
There is no such thing as a typical graphene.
So it's 10 to the. I'm trying to remember. It's 10 to the 12 per. I think it's 10 to the 12 per centimeters.
Okay.
Squared. Yeah. Yeah. Yeah, I always get mix myself up when it's centimeters versus meters. I think it's yeah. Okay. Okay. So there are no more questions on that. Then I'll go to the next effect, which is the first of two acoustic streaming effects I want to discuss. And so this one is called Eckart streaming. And so on the left, we have an example of Eckart streaming in the classical setting, where we have this ultrasound transducer just vibrating back and forth and generating, surprisingly, a jet of fluid flow. And so one can imagine making a device which mimics this effect. So you take some rectangular geometry, apply some oscillating voltage to the left contact and ground the right contact, and you're going to look for the generation of some DC current in the sample. Now, to avoid some of the complications of the details of the oscillation modes, we're going to screen the device to make these oscillations as close to acoustic as possible. So to understand where this effect is coming from and why you would generate this parity-breaking jet of fluid flow, as with other frequency conversion effects, we generally think of this in terms of perturbative expansions. And so at leading order, this oscillating voltage will give rise to some kind of traveling wave in my device. Now this traveling wave, because you have resistivity and viscosity and other dissipative mechanisms, it will attenuate. And this is shown by this exponential decay alpha. For simplicity here right now, we're just going to neglect no slip. We're going to ignore the effects of boundary dissipation and focus only on bulk. If you like, this is equivalent to taking a stress-free boundary condition. And then what you do at second order is you take this and you plug it into your convective force, and you find a somewhat surprising result is that this convective force, when time averaged, is actually non-zero. And it depends on how much attenuation I have in my device. So what this tells us at the end of the day is that this jet of fluid is arising due to the fact that I'm generating a DC convective force and driving this DC current flow. This is kind of similar to, say, a solar cell. If you imagine, this oscillating voltage that's coming from some electromagnetic radiation, which is generating for you some kind of DC photocurrent. Now, one of the differences, however, from a typical solar cell, say a PN junction, is that while in a PN junction your parity breaking is coming from the fact that you have P and N, the material itself is parity breaking. Here, what's breaking parity is the fact that I have dissipation in the system and I have asymmetric boundary conditions. So, the left has oscillating voltage and the right is grounded. Okay. So, to understand some of the functional features of this DC current generation, here I have plotted the DC current against the length of the device. And at long lengths, we find 1/L type behavior. And so this is typical conductor type behavior, where you can kind of imagine that this DC convective force is providing some sort of effective voltage. So you have some net DC current drop across the device. At short distances, the reason you get these oscillations is because there's interference coming from reflections from the far contact. And so just to go ahead and estimate this in graphene again, so for device length 50 micrometers, frequency 1 terahertz, and this puts us in this long device linear regime, what you get is about 1 nanoamp of current for 24 microamps of current amplitude. And just to kind of emphasize further that these interference oscillations are quite small, for an even shorter device of 20 micrometers, if I plot the DC current against the frequency and then look at these oscillations again, these oscillations are maybe 3% of my DC current. So we're talking about picoamps of DC current if the total DC current is about 1 nanoamp. Okay. Yeah. So before I move on to the next thing, are there any questions on Eckart streaming? All right. Okay, so last but not least, we turn to what's known as Rayleigh streaming, and this is a boundary dissipation effect. So as opposed to the previous one where we focused on the bulk, in this case, I'm going to assume there's no attenuation mechanisms, or at least they're very weak in the bulk. So we're going to imagine imposing some standing wave of velocity of the following form. And for simplicity, I'm just going to assume that the total DC current through the sample is 0. And so this is equivalent to having a pipe with 2 closed ends. Now, of course, this longitudinal standing wave ansatz has no y dependence, and in particular doesn't vanish on the walls of my device. So you're going to need a transverse component of velocity to account for the no-slip condition. And so you add this to satisfy the boundary conditions. And then you go and run the same game of evaluating the convective force, time averaging, and again, you get something that is non-zero. And there are two features to this convective force in this case. The first thing is that you see there's an exponential decay from the wall. This comes from the fact that these transverse velocity contributions needed to satisfy no slip are localized to the wall, and the dissipation in general is going to be localized to the walls. So that's this is why you have this. And then you get a half period simply from the fact that you have a quadratic nonlinearity in the convection force. And so this will also lead to some sort of streaming currents in my sample. And what I will argue to you is that this force will lead to this repeating pattern of circulating current cells, which is divided in half across the x equals 0 plane, and then it's going to repeat with the half the periodicity of the standing waves. Okay, so to see where this comes from, we can divide our system into bulk and boundary layer regions where the convective force are separated by the strength of the convective force. So in the boundary layer region, as we've seen in the Eckart streaming section, this will lead to some net streaming flow, where on the boundary, you'll have 0 to satisfy no slip, and then this velocity increases away from the boundary. And then it turns out at this interface, the velocity is going to be some v slip, some non-zero value. Now this sets up the boundary condition for the bulk, and since we have current conservation and the fact that net DC current is 0, any current that exists in the bulk must circulate, right? And this is precisely what gives rise to these circulating current cells that I had discussed previously. This result was somewhat surprising to us because one would expect, well, convective forces are localized to the boundary. Everything that would be interesting is isolated to some boundary layer, but yet this these effects actually end up being propagated into the bulk and give you measurable type effects. So of course, with circulating currents, you can ask about how much magnetization is in my sample. Can you actually see this? And so again, we take graphene. If we have an input frequency of 2 terahertz, we expect to see DC magnetic fields of order 10 to the minus 10 Tesla for roughly microamps of current. And if you position your magnetometer about 1 micrometer from the sample, right? Yeah. So So with that, I'd just like to conclude. So I've argued to you that, and hopefully convinced you that linearized hydrodynamics, on the face of it, it looks very similar to Ohm's law, and so it's very difficult to distinguish without additional probes such as those that have been mentioned earlier: temperature, magnetic field carrier dependence. In essence, looking carefully at the details of the microscopics of various scattering mechanisms. So instead, what we're proposing is to take a different tack. and to ask how is hydrodynamics different from Ohm's law, and in particular looking at effects that are generated by nonlinear convection, which leads to these three effects that I discussed. It would be interesting to kind of continue this program of looking at nonlinear effects and looking at what additional phenomena that would be distinctive in the electron hydrodynamic regime. In particular, these effects are all coming from the classical setting, translating the classical setting over to the electron hydro setting, and there may be more interesting interplays between the various terms, because you have this additional resistivity, and we've seen hints of this in some of our calculations. So for instance, there's looking at some of these instabilities close to that critical point in V naught in this Bernoulli device is something that we are interested in looking into. But yeah, thanks for everybody's time and attention, and I'd be happy to take any more questions that anybody has.
Thanks, Aaron. So are there questions? There have already been quite a few, but I'm pretty sure there are more.
Maybe I'll just make a comment.
Sure.
So the first statement here, linear hydro equivalent to Ohm's law. Ohm's law, of course, sometimes people mean different things under the actual Ohm's law, right?
Sure.
So the statement that sometimes is meant that it's just simply current equal to conductivity times electric field, right? Sometimes meant by Ohm's law, but that is simply linear response. So whichever theory you're going to have, whichever scattering mechanism you're going to have, if you are within linear response, that's what you're going to get.
That's right.
So
that's right.
From that viewpoint, of course, you can't distinguish dynamic from non-hydrodynamic, right? Because you are linear response.
Right. Yeah, I totally agree.
Okay, more questions. Maybe I can ask one. Like, to me, it wasn't quite clear, like where the specifics of graphene came in. Like, I mean, graphene is not just a 2-deck, and like in the first part, you talked about 2-dimensional electron gas, but graphene has a number of special properties.
Right. So
where exactly kicked that in?
Yeah. So I guess I should have mentioned this before. So I have chosen graphene as a model system. I'm imagining working with graphene not terribly close to the charge neutrality point, so that you don't have to worry about these additional features you're talking about associated with the drop point. Indeed, these effects I expect also to be observable in some of the 3-dimensional hydrodynamic materials that people are talking about, palladium cobalt oxide and the other candidates. So this is not graphene specific. I guess one thing is that the reason that graphene was chosen as kind of the model to do all of these estimates is due to the fact that graphene has relatively low carrier density compared to the other devices, and as a result, it's easier to achieve higher Reynolds numbers in these devices without melting the device. All these proposals require some pretty large currents, and so graphene just is the easiest to observe some of these effects.
Are there further questions?
Perhaps, if I may ask a question, I'm sorry I was late, so I really hope that you didn't explained that before. I was wondering how much these experiments and these proposals and, well, the things you got out of your theory are dependent on this thing to be clean. So, you know, if you have inhomogeneity or defects that perhaps are artificially induced in this on different length scales, how would that influence your results?
Right. So if you so if you believe you're in a hydrodynamic regime, let me put it this way: all of these results were derived assuming that you're already in the hydrodynamic regime. So you have to be clean enough that you're looking at length scales where that is valid. Once you have that, you know, you could the other issues of disorder or inhomogeneities, they come into they're basically absorbed into gamma here, right? And so since gamma is what controls the strength of this Reynolds number here, it would essentially kill the nonlinear effect if gamma is too strong. And so you do want it to be clean, clean enough so that your Reynolds numbers are not so small that your nonlinear effects are not observable. That's how it would feature.
But if I understood this correctly, this is for small defects that would be absorbed in this gamma. If you would have like big defects that you know your liquid basically flows around, it would have a different.
Yeah. So if you have like, I see what you're saying. So if you have like large.
Do I misunderstand?
No. So if you have large type defects, these effects, how do I want to say this? I think it depends on so those are the more geometry type effects. So for instance, this Eckart streaming setting, I wouldn't expect this to so it would affect, for instance, the first order solution of these, and you'd have geometric type corrections, but I guess the general character of generating some DC current would still persist. Is that what you're asking?
Yes.
Yeah. Okay.
Thanks.
May I ask another question?
Mm-hmm.
Okay, so you started this talk with the sigma 2 term,
yep,
right? And then you went to discuss other things. So
yes,
is there any relation, or maybe it's obvious and I just
yeah. So
okay.
I think the point of the first half was to say we want to move out of linear response, because I get, at least from our perspective, linear response is, there's a lot of microscopic details that may be difficult to actually see and maybe actually difficult to see and distinguish between different scattering mechanisms. Now, in this, the second half, the sigma 2 or which we're equating to this new coefficient here, it's present but not super important. So a lot of kind of the issues that we raised previously about sigma 2 are not really present in this approach.
Thank you.
Are there any further questions? Well, if not, let me thank Aaron again. And so in 2 weeks, David Rodriguez from Leiden will be our speaker. He will talk about hydrodynamics in 2+1 dimensional systems and Hall viscosity.
Yes.
And yeah, hope to see all of you there. Afterwards, we will switch from the two-week rhythm, because otherwise we collide with the March meeting, which we try to avoid. Okay, I will also post the video of this later on the website, and we also have a YouTube channel of our institute where I will post it. So if you want to review some of it. So yeah, thanks to all of you. Have a good evening. Have a good day wherever you are. See you around. Bye.